All right, let's talk about AI. We see all these incredible things happening with machine learning, right? But what's the real secret sauce? Well, I'll tell you. It's not just about writing some super fancy algorithm, it's about taming the data beast. We're going to talk about the true unsung hero of machine learning, data preparation. So let's get into it. So here's our game plan. First, we'll uncover what the real work of AI actually looks like. Then, we're going to walk through the data scientist's playbook, how we teach machines to understand categories, how we level the playing field for all our numbers, and how we deal with the messy gaps and glitches you always find in real data. We'll even look at turning plain old sentences into signals a machine can use. And then we'll pull it all together and see why this is the true foundation of intelligence. Okay, Section 1, the real work of AI. So when you picture someone building an AI, you're probably thinking of a coder, headphones on, writing pages and pages of complex algorithms. And yeah, that's part of the story, but it's not the main part, not even close. This quote right here, it hits the nail on the head. The vast majority of the time, the real grind is spent cleaning, shaping, and getting the data ready before any fancy algorithm ever gets a peek at it. Every amazing AI you've ever seen is built on top of this careful and honestly painstaking work. So let's tackle our first big challenge. Section 2, teaching machines categories. See, our models, they only speak one language, math. They live in a world of numbers, but we live in a world of words, of categories. So how on earth do we bridge that gap? Let's make this real. Imagine you've got a data set with a simple column for country. A machine learning model has no idea what to do with the words India or Canada. So what's the first thing you might think of? Well, maybe just assign a number to each one. But if we do that, say India is 1, Canada is 2, and Brazil is 3, we've just created a huge problem. The model, in its purely logical brain, now thinks that Brazil is somehow greater than Canada just because 3 is a bigger number than 2. It's implying an order that just doesn't exist, and it would totally poison your model's understanding of the world. So, we obviously need a smarter way, and that's where a technique called one-hot encoding comes in. The best way to think about it is like a big control panel. You've got a separate light switch for every single country. For any person in your data, you just flip on the switch for their country and leave all the others off. And boom, this is what that looks like. Every country gets its own column. A 1 means, yep, this is the one, and a 0 means, nope, not this one. Now, the model sees each country as a distinct option, not part of some weird, nonsensical ranking. It's a clean, honest, numerical way to represent categories. But of course, there's always a catch. What if you have a feature with hundreds or even thousands of categories? Like, say, every city in a country. You'd suddenly create thousands of new columns, and for any given row, almost all of them would be zeros. This is what we call sparsity, and it can make your dataset absolutely massive and slow. For those situations, other techniques like binary encoding can be a better tool for the job. Okay, so we've sorted out the words, but what about the numbers themselves? This brings us to a whole new problem. We've got to level the playing field, because trust me, not all numbers are treated equally by a machine. Just take a look at this. You might have someone's age, which is 35, and their salary, which is $95,000. To us, those are just two different facts. But an algorithm sees 95,000 and 35, and it thinks, whoa, that salary number is huge. It must be way, way more important than age. It gets biased by the sheer scale of the numbers. To fix this, we have to scale our features. Put everything on the same yardstick. There are two main ways to do it: normalization and standardization. Normalization basically just squishes all your data into a set range, usually between 0 and 1. It's simple, but if you have one really extreme value, an outlier, it can warp the whole scale. Standardization is a little different. It rescales your data based on the average and the spread. This makes it way less sensitive to those weird outliers, and it's perfect for data that looks like a classic bell curve. All right, now for the part that every data scientist has to master, the messy reality of the real world, handling gaps and glitches. And honestly, this is where so many projects succeed or fail. No real-world dataset is ever perfect. You're always going to have missing pieces and weird values that can throw a monkey wrench into your whole system. Just look at this. We've got a missing age value, which we see here as NaN. That just stands for not a number. But missing data is sneaky. It can hide as a blank space, the word null, or even something a user typed in, like, I don't know. So, your first job is always to play detective and hunt down all these hidden gaps. So, once you find a gap, what do? Well, you could just delete the entire row, but then you're throwing away all the other good information in that row. A lot of the time, a better move is to impute, which is just a fancy word for filling it in with a smart guess. You could use the average age of everyone in the dataset, but a much smarter guess would be to look at only the other retired people and use their average age to fill in the blank. That's a way more logical and accurate guess, right? And this is just so important to understand. There is no magic perfect solution for missing data. If you delete data, you're losing information. If you fill in data, you're adding a little bit of your own bias. It is always a trade-off, and you have to think critically about what makes the most sense for what you're trying to build. The other kind of glitch you have to watch out for is the outlier. This is that one data point that's just bizarre. It's so far outside the norm that it can act like a giant magnet, pulling your entire model's predictions way off course. Think about it. If you're predicting house prices and someone accidentally typed in $20 million instead of 200,000, that single typo would make all your other predictions completely worthless. So how do you find these things? Well, remember standardization? That z-score it calculates is an amazing tool for this. It essentially tells you how many standard steps away from the average a data point is. And a good rule of thumb is that in most datasets, anything that's more than 3 of those steps away from the average is waving a big red flag, basically screaming, hey, I might be an outlier.
Okay, so we've wrangled our categories, we've leveled our numbers, and we've handled the glitches. But what about just text? Sentences from a customer review or paragraphs from an article. How do you turn that into numbers? Well, this brings us to a huge field, but let's look at one of the most classic and important techniques.
So a really powerful way to find the most important words in a document is a score called TF-IDF. Let's just break that down. The TF part is term frequency, and it's exactly what it sounds like. You just count how many times a word appears in this one document. If it appears a lot, it has a high TF score. It's important to this specific piece of text. But you might be thinking words like the, and, or is are going to appear all the time, and they don't mean much. And you're exactly right. That's where the IDF part comes in, inverse document frequency. Think of this as a rarity score. It looks across your entire collection of documents and asks, is this word common or is it rare? Super common words get a low score. Rare, specialized words get a high score. And then you just multiply them together. Term frequency times inverse document frequency. The result is pure gold. It gives the highest scores to words that are used a lot in this specific document, but are very rare across all the other documents. And those are your keywords. Those are the words that really define what a document is all about. And that brings us to the home stretch, the big takeaway, the foundation. We've gone on this whole journey of cleaning, transforming, and structuring data. So, why? Why do we go through all this trouble? What's the point? Well, it all comes down to a classic saying, garbage in, garbage out. You can have the smartest, most powerful algorithm in the world, but if you feed it messy, inconsistent, garbage data, you will get garbage results every single time. The quality of an AI model is ultimately defined by the quality of its data. So I'll leave you with the final thought to chew on. Is what we call artificial intelligence really just a testament to the incredible power of extremely well-prepared data? Something to think about. Thanks for watching.